Hello, Georgi Romanic here. Today we will continue with the physics of torques. In today's video, we will tackle one very specific problem, but problem that can be generalized to so many different situations in real life. In particular, we will analyze what holds this plant attached to the wall and how that structural stability is achieved. So, first, let's see how this configuration looks like, and then we will set up the problem and then solve it. The structure that we are investigating is this plant that is attached at the end of this wooden stick. This wooden stick is 30 centimeters long, and the plant is attached here 2 centimeters away from the end. The diameter of the stick is 2.5 centimeters. The mass of this plant is around 450 grams. What we need to calculate now is the force that the plant and the wooden stick exert on a metal screw that is inside the wall and that is basically holding these two things. Now, when we understand the setup and the problem, let's go and solve it. Here is the sketch of the problem that I just discussed. In black we have the wall, and in the orange we have the wooden stick and the screw inserted into the wall. In green we have plant that is hanging down. The dimensions and masses that I talked about are provided here, with the addition of the angle between the wooden stick and the wall being 70 degrees. I forgot to mention that. Gravity G is 9.8 meter per second square. The suitable pivot point that we want to choose in this problem is right here, at the bottom part of the wooden stick where the stick touches the wall. Let's see why. Both the weight of the wooden stick and the plant are creating positive torque counterclockwise, and the wooden stick would pivot around this point. You can imagine going down around this point over here. At the same time, around this point, we would have negative torque exerted by this metal screw inside the wall that is counterbalancing these two torques due to wooden stick and the plant itself. Now I would like to emphasize that you can choose any pivot point you wish, but it is always suitable, of course, to choose the pivot point that is the best option to solve particular problem. In this case, we want to find this force Fs, force due to the screw inside of the wall, and this turns out to be the most suitable pivot point. Fw is the weight of the wooden stick and Fp is the weight of the plant. I will use the concept of statics, which says that sum of all torques around pivot point, let's call this pivot point Q, needs to be 0. And we are in statics because this plant and wooden stick, and they are not moving. Well, we have two positive torques due to the wooden stick and plant. So torque due to the wooden stick plus torque due to the plant are counterbalanced by the negative torque due to the screw inside the wall. So minus torque due to screw, and that needs to add up to 0. Well, let's first evaluate torque due to the plant. Torque due to plant would be weight of the plant, which is mass of the plant, times G, times the arm of the force. And we said arm of the force, from the pivot point, we drop a normal to the line of action of this force, which would be this. So the line of action of the force is in vertical direction, and therefore let's call this distance R1. So this is the arm of the force for the torque exerted by the plant, plus torque due to the wooden stick would be mass of the wooden stick times G times this So this is the line of the force due to the wooden stick. Therefore, this would be the distance, let's call it R2, that represents the arm force from the pivot point Q to the line of the force FW. And minus torque due to the screw would be force that I am trying to find, Fs, times the arm of the force. Notice in this case, the arm of the force is this. So from point Q, I drop perpendicular to the line of the force, and this is the distance, let's call it R3, and we can see that this distance R3 is already half of the diameter of this wooden stick. So Fs times R3 equals to 0. What we need to find now is these distances R1, R2 and R3. But that shouldn't be that difficult. Because we know this angle alpha, that means that this angle over here also needs to be alpha. So let's zoom in this part over here. We have the wooden stick that has the length L minus small l when it comes to this part where the plant is attached at the end of the wooden stick. And we have this arm force R1. And this over here is angle alpha. This is 90 degrees, so we can already see from here that R1 is simply sine of alpha times the hypotenuse, which is L minus L. Therefore, MP times G times R1, which is L minus L, times sine alpha, plus MW times G times R2. But R2, we can see we can apply the same concept that we had here, but instead of L minus L, I'm using the whole length of the wooden stick, and therefore the arm of this force, R2, is L half times sine alpha, because gravity acts in the center of mass of this wooden stick. And finally, minus Fs that I'm trying to figure out times R3, but R3 is just radius of the wooden stick. And that needs to end up to 0. Now I can rearrange this to solve for Fs, and that ends up organizing this is 2g sine alpha, because I can factor out sine alpha, and g also appears everywhere, and this 2 will go to nominator, times this term here, mass of the plant, L minus L, plus mass of the wooden stick times L half, and everything divided by D. If I plug in these numbers and we have them over here, I get that the force is 102 newtons. How convenient. Almost exactly 100 newtons. Now let's please analyze quickly this final equation, because it is very informative. We see if gravity increases, if we are, for example, on Jupiter, then the force exerted on the screw would be higher. That makes sense. As the angle alpha increases, sine of alpha increases, which means that the force increases. And that is also logical. If this wooden stick was 90 degrees, you intuitively can conclude that the force would be higher than if it was very vertical. Of course, if masses of the wooden stick or plant increase, the force exerted on the screw also increases. And the same goes with the length of the stick. However, if the plant is attached closer to the wall, the force exerted on the screw is smaller because we are subtracting this from the total length of the wooden stick. And interestingly, the thicker the wooden stick, the better, because the pivot point goes down if diameter increases, and then the arm of the force Fs that is creating this negative torque increases, which means the stability of this structure increases too. 100 newtons is not so large force, so we can conclude that there is not that much force exerted on this screw over here. I hope this video deepened your understanding of torques and the concept of statics, and also showed you how you can use these concepts to solve some real problems in everyday life around you. Before purchasing this plant, I carried out detailed structural analysis of the stability of this structure. It's a 300-page study because the stability of my plant must not be jeopardized. Thanks for watching. Until next video, goodbye.